our last type of reaction, combustion reaction. So we are on the fifth and final type. So the first four types of reactions, we were using our reds and our blues, and we were single people and couples and breaking up and cheating and all of the fun stuff. Combustion reactions, we get to take a break from our red and blue colored periodic table. In fact, we don't even really need to use our periodic table at all, which is a very rare thing for me to say in chemistry class, because combustion reactions are a very specific type of category where I'm actually not looking whether I'm red or blue, but I'm looking for specific things on my reactant side and on my product side. So a combustion reaction, you'll know one when you see one, when you got some sort of CNH thing and oxygen. If you see those two things as your reactants, you can completely ignore the couples, the relationship drama, and start blasting out carbon dioxide and water as your products. You've got a combustion reaction. Okay, a combustion reaction is a reaction where a hydrocarbon or an alcohol, we'll show you some examples of what an alcohol looks like. It also has carbons and hydrogens in it, so it's not that much of a stretch. But when it reacts with oxygen after a lot of heat or fire is added to form carbon dioxide and water. The only is simple, carbon dioxide, water, carbon dioxide, water. You do not have to use your brain. The only tricky part about combustion reactions is balancing them. So that is basically what the majority of our lesson on working through these practice problems today is going to tackle, is getting that balancing thing out of the way. I think I alluded to this in one of our previous videos when we talked just about balancing and not yet into writing our kinds of reactions, but we balance that oxygen last, you guys. Do not with him. He's going to make things confusing. You wait to the very, very end to tackle him. But what we have not yet seen is sometimes in my combustion reactions, after I try to balance oxygen, it is still not wanting to cooperate, that oxygen. So if that's the case, if the oxygens cannot balance, you will then just erase all of the coefficients that you have written and start over. You're like, oh, start over. No, listen, we're okay. You're going to start over by first putting a 2 in front of your original hydrocarbon. Then, like normal, balance your carbons, balance your hydrogens and your oxygens, and it will work out. It works out every time. These are horrible to balance without some sort of a strategy, and luckily this strategy is not a terrible one for us to remember. Okay, so let's start knocking these out. It says complete and balance the reaction for the combustion of the following compounds. Okay, if this is all I have given to you, you know you're going to do a combustion because look, I got something with C's and H's and oxygen. This is going to be combustion, which y'all ready for how simple this is? The two products of a combustion reaction: CO2, water. In fact, if I want, I can write CO2 in water for all of them. CO2 in water. You're like, oh my gosh, but then what makes them different? The only thing that makes them different is what that hydrocarbon is. And as a result of that, the balancing is not all going to be the same on all combustion reactions, which that's why we're basically doing a practice lesson in balancing today. Okay, so let's focus in on this first one. Okay, so this is methane or carbon tetrahydride. So we have burning him in oxygen. We will make carbon dioxide and water. Okay, so balancing. Start by balancing the carbon first. Very excited about that. 1 carbon on this side. We already got 1 carbon on the product side. Great. Balance the hydrogens next. 4 on the reactant side. Ooh, to get 4 hydrogens on the product side, I need to put a 2 in front of that water. Cool. Now, oxygens last. That is going to involve me doing a recount of how many oxygens I have on the product side to figure out what number I have to put there on my O2 as a reactant. So it looks like I have 2 oxygens coming from the carbon dioxide, and I have 2 coming from the water. So I have a total of 4 oxygens on the reactant product side. So I do need 4 on the reactant side. So to get 4 oxygens on the reactant side, I put a 2 there. Great. Okay, let's do the next one. This is super fun. Okay, this is ethyne, I'm pretty sure. Yes, this is ethyne. Y'all are like, I don't know how to do this. If you're my on-level babies, this is totally dicarbon dihydride. Both are acceptable for us. So he's reacting with oxygen, carbon dioxide, and water. Great. Let's do our carbon balancing first. I got 2 here, which means to get 2 carbons over here, put a 2 in front of carbon dioxide. Hydrogens, I got 2 there. Well, I already have 2 on my waters. We feel good about that, right? Okay, so now I got to balance my oxygens. So total oxygens on the product side, I have 4 coming from these 2 molecules of carbon dioxide and 1 coming from that 1 molecule of water. 4 plus 1 is 5. You're like, great. I cannot get 5 on this side if I am always coming in multiples of 2, thanks to the diatomicness of that oxygen. So here we have run into a situation where it's like, I cannot possibly create an odd number of oxygens on this side. Well, if that be the case, if oxygen cannot balance, we will erase all the coefficients and just start over by putting a 2 in front of your hydrocarbon. You were like, you have got to be kidding me. I am not. It's okay. No big deal. Let's just start over. Oxygen got tricky, so let's do this now. All right. Now how many carbons do I have? I got 4. I need 4 carbons on this side by putting a 4 on that side. Hydrogens, I have 4 on the reactant side, so to get 4 on the product side, I now got a 2. Now let's reassess the oxygens and see if they're going to be a little bit more friendly for us. We have 4 times 2, we got 8 oxygens, and 2 oxygens. 8 plus 2, I get 10. Can I get 10 over here by putting a 5 there? So it works every time, which is super exciting. Okay, I want to do the next one with us. So we already know it makes carbon dioxide and water. All these make carbon dioxide and water, carbon dioxide and water. Okay, so I got a little bit more variation here. You're like, that is not a hydrocarbon. It's like, well, it's got carbon and hydrogen, so we can do some combustion with it if I'm making it react with oxygen. But you can sometimes see some oxygen in your hydrocarbon combustible molecule, okay? That hydroxide group here at the end, or that OH group at the end, is a hydroxyl group that makes something be an alcohol. If you were my honors kids, you were like, yep, we know what alcohols are. If you were an on-level kid, you were like, nope, I don't know what that means. It does not matter to you. You see something with C's and H's, you go balance. Carbons first, hydrogens next, save oxygen to the end. Okay, so here we go. We are ready to go. Carbons first. I've got 1 carbon here, 1 carbon here. We're good. Hydrogens, a little bit sneaky. I got to look at all the hydrogens. I got 4 total here on the reactant side. So to get 4 total on the product side, I put a 2 in front of my water. Now I got to figure out my oxygens. My total oxygen count on the product side is 2 plus 2, or 4. That means I need total 4 oxygens here on the reactant side. Here's also something tricky here. I can't just be like, oh great, I'm going to put a 2 there because then that'll get me 4. Well, I've got an oxygen awkwardly here, to where I've got a situation where I've got, now, man, I got some odd numbers of oxygens on the reactant side that I cannot resolve by putting numbers here to get me that 4 that I saw on the product side. So if oxygens be being tricky, erase the coefficients you have placed, start over with a 2 in front of this blank. So now I have 2 carbons. 2 carbons in front of CO2. Now I have 8 hydrogens. So I get a 4 in front of H2O. Recounting my oxygens, I have 4 oxygens from CO2, and I have 4 oxygens from my water molecule, 8 on the product side. What can I do to show 8 oxygens on the reactant side? Well, I already have 2 oxygens here in this hydrocarbon alcohol, right? That means 8 minus 2, I've already gotten 2 here. I just need 6 more coming from my O2 guy. So to get 6 from there, I would put a 3 there. So 8 oxygens on the product side and totally 8 oxygens on the reactant side. It works every time. For funsies, let's do the next one. Y'all, this is the combustion of glucose. This is the reaction that our cells do every single day. They break down our food into glucose, and then that oxygen that we breathe helps break down glucose to release ATP for energy for us, which is also why we discard out carbon dioxide in water. Very exciting. That's a combustion reaction. A teeny tiny little fire is going on in your cells. Very small though. Okay, so let's see. Carbon first. I got 6 on the product or reactant side, so I need 6 CO2s. I got 12 hydrogens on the reactant side, so to get 12 on the products, I will get 6 waters. Recount my oxygens here. Okay, I've got 6 times 2 is, I may have to write some of this out because I feel like I'm doing a lot of mental math in my head. 6 times 2 oxygens will give me, what is this, 12 oxygens? And then I have 6 oxygens here, right? So the total of 12 and 6 is 18. Y'all with me so far? Okay, I love that for us. Now, in my glucose molecule, I do have some oxygens trapped in here. So if I'm wanting to get total 18 on this side, yeah, this may be nice for us, right? I already have 6 trapped in this situation, right? Well, the remaining 12 needs to come from here, right? So can I figure out a number to put in that blank in front of O2 to give me 12? I sure can. I can put a 6 right there. So that is the balanced combustion of glucose. I'm going to do maybe a few, maybe 2 examples underneath the next section, which is, it's a stretch to do anything different than just giving you the ding-dang formulas, because I always make carbon dioxide in water, right, you guys? So let's see. I've got, oh my goodness, I got C8H18 reacts with oxygen. So if I give you this information, you see that hydrocarbon, and I'm telling you who it reacts with. So if you were to write those reactants down, y'all, I don't even need my periodic table. I don't even do a crisscross. I know what I got. I've told you, right? C8H18 reacts with oxygen. Oxygen, single guy. I do have to remember that oxygen is diatomic, so he will always come in 2s. So those are my 2 reactants, and then I am set off, just like what I started you off on some of these previous problems where the formulas were given to you. I see that. That is a combustion reaction. I know I will make carbon dioxide and water, and I will be balancing that in some way. Yes? So for the balancing, I'm like, great, balance the carbons. 8 on this side. To get 8 on this side, I need a 2, or I need an 8, right? My hydrogens, I have 18 on this side, which means I will put a 9 in front of water to get 18 hydrogens. Count up the oxygens. I've got 8 times 2. That is a 16 oxygens from my carbon dioxide. Plus 9. This is getting real scary already. 16 plus 9, that's 25. That is an odd number that I cannot resolve by putting a simple coefficient in front of O2. Go start over. Get rid of your 8. Get rid of your 9. So I got a 2. Let's see what we do now. I have 16 carbons. So I will do 16 carbons in my 16 carbon dioxide molecules. 2 times 18 is, oh boy, 36, right? So if I need 36 hydrogens, that just means I put an 18 in front of the water, because 18 times 2 is my 36. I'm really hoping that's right, or else I'm going to seem really silly. I think that's right. Okay. Now we got a lot of oxygens here. We have 16 times 2. I'm going to have to write this out. 16 times 2 gives you 32 oxygens from this guy. And then 18 gives me 18 from this guy. So my total on this end, right, is 32 plus 18. I'm hoping that gives us 50 total oxygens. So I can get 50 total oxygens on the product side by putting a 25, right? And y'all are like, oh my gosh, those are ginormous ratios, or ginormous numbers. Yeah, I agree, but I cannot reduce those numbers down anymore because I have this really limiting odd number of a 25 that prevents me from really getting those down to even lower ratio numbers. Yeah, I'll do one more of these because these are, you know. Sometimes to represent a combustion reaction, I'll just say something burns. And so when you see something burns, that is a fancy way of saying it's forcing it to react with oxygen. React with oxygen. So oxygen is in the air, and when I burn something, that oxygen is actually being used up when I'm burning a hydrocarbon. So we are good to go. We know that we are taking this guy. This is propane for my honors kids, and he is reacting with oxygen. We are like, cool, we will always make carbon dioxide and water. The only thing sneaky is my balancing, but we are ready to go. We have got 3 carbons on the reactant side, so I will use 3 CO2s. We have 8 hydrogens on the reactant side, so I will put 4 waters. Okay, recount the oxygens on the product side. I have 6 here and 4 here, so 10 total oxygens. So to get 10 total oxygens on the reactant side, I will put a 5 in front of my O2 molecule. So this is not terrible, honestly, at all. The only terrible part about my combustion reactions are we got some balancing issues, but is my only one of my 5 types where my skeleton does not involve letters of the alphabet like A, B, C, and D, where you can substitute actual elements and lots of different kinds of elements from your periodic table into those positions. These I'm looking for specific things, and more specifically on the specific things, 3 out of the 4 have got to look exactly like this. The only component in the reaction equation where you are allowed some variation is whatever conglomeration of that hydrocarbon has in terms of carbons and hydrogens and potentially sometimes some oxygens as well. This is our last of our 5 types of reactions. We now know how to write our own reactions for all of my 5 types, predicting the products based on what type of reactants I've seen and balancing at the end.